Now, if you have ever wondered how a sunglass works, or a polarized sunglass, how it works, or how the intensity of light changes as it passes through certain filters. Now, at the end of this video, we are going to be explaining that concept using Malus's law. All right. So now, what is Malus's law? Malus's law was propounded by Louis Louis Malus. Louis Malus. Louis Malus in the year 1808. All right. So, and his law is crucial to understanding polarization property of light. So, the law helps us to study the light intensity in relation to the polarizer or analyzer. Now, the concept is such that it was named after Asian Louis Malus, like I said, and it is such that as light passes through a polarizer, two polarizers basically, and the second polarizer is rotated, the intensity of that light changes. The intensity of that light changes. Okay, so now, when a plane polarized light is seen through an analyzer is just another polarizer. The intensity of transmitted light varies as the analyzer is rotated through an angle perpendicular to the incident direction. That is, if the light is rotated, if the plane, in case you don't know what polarization is first, let me try to do justice to that. Now, polarization simply, light simply is made of is the way we perceive electromagnetic wave and electric the electric field and magnetic field of the earth that are moving in a direction that is perpendicular to each other. So the way we perceive both is through light. Is that okay? So light simply is an electromagnetic wave. Okay. So, and we know already from here now that the electromagnetic wave travels in, consists of two waves traveling in perpendicular directions. That is the electric wave and the magnetic wave. Okay, so a polarizer, therefore, is a substance, or polarization of light force is making that beam of making a beam of light to travel in one plane, making beam of light to travel in one plane, since we know here that it is traveling in several planes. Okay, so um the idea is that a polarizer causes that light to travel in only one direction. So what it does is that it's going to absorb one of the directions and leave the other direction to pass through successfully. So, for example, if I use a polarizer that the direction of transmission is perpendicular to this one here, which means it to be parallel to the vertical moving wave, then it means that the aperture here is going to be in the vertical direction. So the wave we are going to see immediately after this polarizer is going to look something like this. So it would have absorbed this other wave here, to have absorbed this wave here in yellow, to have absorbed it. Okay, so that is basically the principle of polarization. All right, now, so the case is now where we use two polarizers, So this is the first polarizer here. Here's the first polarizer, and light is moving in this direction and in this direction. Okay. Now, if the direction of transmission of this plane of transmission of this polarizer is in the vertical direction, then the wave we are going to see at the end of the day is going to be this. Okay. So when that plane polarized light now goes in this direction, so we're going to see only one plane. We're going to see a plain polarized light. Okay, so if we place another slit, if another slit is placed here, another polarizer rather is placed here. Okay, if another polarizer is placed in this direction. Okay, now here's what happens. This second polarizer will be called an analyzer. Why? Because we are going to be using it to analyze the intensity of the plane polarized light. This is our plane polarized light now. So by the time it moves into this slit, I will begin to rotate this slit. Here's what happens. The intensity of this guy, by the time it will of this plane polarized light is let's represent it using I naught. So by the time it moves out of this slit, what we're going to see is the same. If it were in this direction, the intensity will be the same. But if we rotated this guy, that is the analyzer, if the analyzer is rotated in a particular direction, such that it creates an angle theta, so that it creates an angle theta. Okay, now here is what happens. The intensity that is gotten at the back here, the intensity, let's say we rotated this analyzer in that direction, so the emerging ray will now look something like this. Okay, the intensity of this polarized light here is going to be given by I, is going to be directly proportional to the square of the cosine of the angle between the plane of the original plane of the analyzer and the plane to which it is rotated. The plane to which it is rotated. All right. So we say mathematically it is given by I, that is the new intensity of the light, is directly proportional to cos squared theta. Is that clear? Is directly proportional to cos squared theta. Now if we were to input a constant here, mathematically it becomes I equals what? The constant is going to be I naught cos squared theta. Now this can be proven in another way. Remember that we said that the amplitude of light, the intensity of light is directly proportional. The intensity of light is directly proportional to the square of amplitude, isn't it? Is directly proportional to the square of the amplitude of the light wave. Okay, so if this is the case, then we can say that we can easily use this convention to describe this phenomenon of Malus's law. You know that the plane so let's say the plane polarized light is like this and it moves out of this place. Now by the time this guy is rotated, its plane of transmission will be a straight line around here, but after rotation, its plane of transmission will move somewhere in this direction. So if it moves in this direction, what will happen is that the amplitude of that light would have changed. The amplitude of the wave that comes out of this slit would have changed. So that this theta here, it has moved by an angle theta, it has rotated by at an angle theta, and that plane, that amplitude that is now created would have changed. Now that is very simple. Let me show another way to visualize that. So that light was traveling in this amplitude. This is amplitude. By the time it is rotated, it's going to be rotated in this direction, isn't it? So the amplitude A here will become the amplitude A here. So this is the amplitude. But notice that this is going to be taller. Let me redraw that. Now primarily this is going to be taller. So we are going to see that if the light was as tall as this before, the light that was as tall as this before, the amplitude that was as tall as this, let me just use that word so that you understand, trying to use simplistic terms here. So that amplitude was as tall as this will now become as short as this. Does that make sense? This is the new amplitude of the wave of the plane polarized light that is coming out. So let's call that new amplitude. The former amplitude, let's call it A sub naught. So we'll call that A sub naught. And so if I rotated this arm guy by this angle theta here, let's call that place theta, by angle theta here, then it means that this guy has moved. You know that this length is going to be the length of this guy, isn't it? So it means that this place is also a sub naught. Does that make sense? Then this new amplitude that is created here, this new amplitude that is created here from here to here is going to be our new A. Does that make sense? Okay, so we have made a triangle out of this. We have made something that looks like this. So here is A sub naught, here is A, and here is our 90-degree angle. A 90-degree angle. Since this line is parallel to this line, then this place must also be theta. Okay, so what we have is, what we are going to have eventually is something that looks like this. What we're going to have at the end of the day is something that looks like this, with this being angle theta and our initial amplitude A sub naught and our new amplitude A. Okay, so if this is a 90-degree angle, then we know that our new amplitude A is going to be the relationship. This our new amplitude A is going to be the adjacent, and the long side is going to be the hypotenuse. So the relationship between those is is cosine, isn't it? So it means that cosine of theta, it means that cosine, that is cos theta, is going to be what? Adjacent, which is A, over hypotenuse, which is A sub naught. Okay, by the time we want to make A subject, by the time we make A subject of formula, then we're going to come up with an equation that looks like this. A will be equal to A sub naught cos theta. Now if we square both sides of this equation, we're going to have A squared here and A squared, everything here squared. Okay, so eventually we're going to come up with this, that A squared will be equal to A sub naught squared cos squared theta. Okay, now remember that we have said initially that our I is directly proportional to what? A squared, isn't it? Okay, now if that is the case, therefore I sub naught will also be directly proportional to I sub naught would directly proportional to the A sub naught squared, isn't it? Okay, so by the time we make it mathematical expression, it becomes I will be equal to K A squared, and here I sub naught will be equal to K A sub naught squared, isn't it? Okay, so we can now make A squared, we can substitute A squared into the equation. By the time we substitute A squared into the equation, then we have that I to then be equal to I sub naught, constant will cancel out, cos theta. Is that clear? Because it's going to be you remember that A squared is going to be I over K, and A naught squared is going to be I naught over I sub naught over K. So K takes care of K. Is that okay? So cos squared, sorry. So this is the proof of Malus's, mathematical proof of Malus's law. But let me show you that in context. So we are going to see in this slide that our light, unpolarized light, is here. It passes through the first polarizer. Okay, it passes through the first polarizer. This is the first polarizer here, sorry. It passes through the first polarizer. So by the time it passes through the first polarizer, it produces a plane polarized light. Now in the second polarizer, we now see the second polarizer being moved at a particular angle theta. So you see, we rotate at a particular angle theta. E here is a vector representing amplitude. Is that okay? E represents amplitude here. So in this case, you are going to see that the angle is angle theta here, and by the time you create a vector of both amplitudes, then what you're going to have is I is going to be directly proportional to A cos squared of theta. Okay, we use amplitude here again. So basically A is amplitude, but in this case, this E2, this E that is used here means amplitude. In case you're confused, this E also means amplitude. Okay, so You know, the amplitude is the maximum displacement of the wave, isn't it? The maximum displacement of the wave um, about its fixed point. Okay, so in this case, we said that the I is going to be equal to is going to be directly proportional to the square of the cosine of the angle between the axes of transmission, the two axes of transmission, the rotated axis of transmission and the second and the original axis of transmission. Now let us consider that the transmission axis of the polarizer and the analyzer are inclined by an angle theta as shown, and let I naught be the intensity and B the amplitude of the electric vector transmitted by the polarizer. The amplitude A of the incident ray has two rectangular components, as you can see here. So it has two rectangular components, this and this, isn't it? Okay, so you have two rectangular components there. Okay, so it says that so we have A cos theta and A sin theta. So that is, if you resolve this guy in this direction here, if you were to resolve this guy in this direction, that will be A cos theta or E cos theta. And if you resolve in this direction, that will be E sin theta, isn't it? Because you open the angle. When you open an angle, I said you should use sine, remember? So A sin theta, and if you close this angle here, you resolve in this vertical component to be A cos theta. But we are particular about the vertical component here. Why? Because that's the original axis of transmission of the polarizer before it was rotated. Now only the Y component, that is A cos theta, will be transmitted by the analyzer, isn't it? So the intensity of light transmitted from the analyzer is proportional to the square of the component of amplitude transmitted by the analyzer. Okay, so what I say basically is that I, as we said, I is proportional to A cos square theta. That is, by the time we bring in that, you know that A cos square theta came from, you know that I is already directly proportional to A squared, isn't it? So if A is just, if amplitude were just amplitude, we have not squared it yet. By the time we want to get the new amplitude there, when we resolve that guy to the vertical components that we did the other, that I showed you just now, if we resolve, and this angle theta, by the time you resolve this to the vertical component, you are going to get that A will now be A cos theta. So by the time you input it into this equation, it will become I is proportional to A cos theta all squared, isn't it? So you input your constant of proportionality and you find out that I will be equal to I naught, I sub naught cos squared theta. Okay? So that will be it for this video. Do want to subscribe to the channel. God bless you.